Okay, I'm going to talk about flow rates, and the first one is volume flow rate. And this is where the derivation of this equation, this is like in units of, could be gallons per second or cubic meters per hour, um, units or cubic feet per minute, something like that. And the way it works, how you actually come out and derive this equation, this is the cross-sectional area times the velocity. It's basically, you think about, let's say a cylinder, right? And let's say this is a cylinder that represents a certain volume. It would be this distance times this area, the cross-sectional area of this, okay? Which is pi r squared for a cylinder. So that will give you a certain volume of your fluid, okay? So if you think about this total volume, that's this, essentially. This is the volume, which is just A times D. And the volume flow rate is basically that volume per unit time. Thinking about this whole cylinder going past some point, let's say P, in some unit of time. Could be per second or minute, hour, or something. And what we recognize when we change it to AD, what happens is this D over T is just distance per unit time, which is velocity. So if you're thinking about, like, this cylinder is traveling, this is a length of, let's say, 1 meter, and it's traveling 1 meter per second, would mean that this quantity of, or this volume would go by this point P, or, this saying this point being this like cross-sectional area at this point P. If it's 1 meter long, and it has a velocity 1 meter per second, it basically is taking this whole volume and going past this point every second, okay? And that's really essentially what you're doing, and that's why it's the velocity times this at the end, okay? So it's just going to be cross-sectional area. How fast does it travel gives you the volume flow rate, okay? Mass flow rate can be found just by multiplying the density times the volume flow rate, okay? So that's just simply that. Mass flow rate. Density. Remember, density is in terms of mass per unit volume. Okay. So then what you would end up with in the final equation here, if you put in this mass per, or at least the units, mass per unit volume times a volume per time, then it comes out to be mass divided by time. Okay. Okay. Another thing related to mass, we have to be concerned. Many of these problems following the conservation of mass. Conservation of mass basically means you have to account for all the mass, right? So like in this case, you have some mass going in, you have mass going out. What's the change in terms of the mass inside of the system would be just delta M of the system. In terms of rates, so the rate at which mass comes in minus the rate at which mass leaves gives you the rate at which it's changing, the mass is changing in the system. And you see it's written as a derivative here. You could also write this for our case if it's constant, if it's, constant rates. This could be delta M system over delta T, okay? All right, we'll take a look at systems with that. And then one more part of this is pipe junctions, right? And the mass flow rates enter junction is 0, right? So what would happen here is that you would have M1 coming in, which would be positive, M2 would be negative, and M3 would be negative. So that would be all summed to 0. So of course, whatever's coming in here is going to be equal to the summation of whatever's leaving here at a Y junction, right? So that's pretty much it. And this is the last of the new material for the class. And we'll take a look at some problems with each of these concepts, all right, related to, volume flow rate and mass flow rate and the conservation of mass, okay? So we looked at fluid statics and fluid dynamics here, and then we used this idea of conservation of mass, all right? So that's pretty much it. Now it's a matter of applying those concepts to solving different problems.